the host anymore?
I'm co-host. It's okay. You can
I
just...
see. Fine. Okay. Okay. So thanks once again. And as I said, this is all meant to be, a pedagogical instruction, introduction to some of these ideas. So if some of this is too elementary or it's too simple, or some of you have seen this before, just stop me, and I'm happy to go much faster. Okay. So what I want to discuss today, I want to start by discussing the properties of asymptotic algebras. In ADS and in flat space. Okay. Now, why is it of interest to discuss asymptotic algebras? So, often in a local quantum field theory, we discuss algebras which are associated to regions in space. Okay, so often in LQFT, we often discuss algebras at so, there's some region, and, we talk about the algebra basically means that we talk about the set of observables that are in that region. So, you might have some field, there might be some points here, and, you might have some field phi of x1, and then you'll have some algebra which is associated with R, which basically consists of, products of this kind. And so on. Now, I should say maybe a disclaimer at the start of this. The people who are really thinking about algebraic QFT would not like what I've just written, because they always like to think about bounded operators. And so I'm going to be a little, sloppy about very high levels of mathematical precision. And I'm going to think more in some physicist terms. And so the algebras we'll talk about will often be these kinds of polynomial algebras of the kind that I've written down. Okay, so in LQFT, we often discuss algebras which are associated to some geometric regions. And this is, something of interest, and you can, there's a lot of work that has been done on this. However, in a theory of gravity, it is often hard, and in fact, this is one of the objects. Okay, it's often hard to specify the position of an observable. So there are often many ways of associating some algebra with the region R. And, it might be that some of them are more natural than others, and some are not. And more than that, it might also happen that in a theory of gravity, we have to contend with the fact that the spacetime itself might be fluctuating, and in some cases might be fluctuating significantly. And therefore, this region R itself might in some states not even have a well-defined geometric meaning. Okay? And so it's not so convenient, often in gravity, to speak of algebras associated with local bulk regions R. I'll try and describe maybe at the end of the lecture tomorrow how this can sometimes be done. But in a theory of gravity, it's often not possible, or it's often not natural, or depends on conventions to specify what one means by the algebra associated with the region R. So it is often unnatural to discuss algebras corresponding to local bulk regions. Okay. However, even in gravity, this is sorry, on my screen here, I only see corresponding, and I wrote beyond that, but it has not shown up.
Yeah, it's not shown. It's not.
Oh, but why is that happening? Sorry, I'm really sorry about this.
No, it hung, is it?
Huh?
Yeah.
This is. Yeah.
I will make you co-host again once.
Yeah, sorry, this is some
Oh.
problem with my iPad, which is just not able to connect to the net. Actually, I don't know why it's not working. Maybe I'll put it on a hotspot.
Let's see.
Sorry, guys. I did connect to this. Activate your network. Oh, 1 second, 1 second. Maybe the problem was I had not activated something. 1 second, let's try again. Sorry, guys, I'm really sorry about this.
No, it's fine. Is it connected now? So with the iPad or?
Yeah, no, it was actually, I don't know why my iPad is for some reason. I think maybe they've stopped recognizing it in ICTS or something.
Oh.
So it's not work. 1 second. Let me try again. I'm trying to connect as a guest, but let's see if it works this time. Hopefully it'll work. Please work. Okay, let's see if it works now. Okay, it's working now. Okay.
Oh, it connected?
Yeah, I think it's working now. Let me just join
think,
the meeting again. Six. Okay, it's come again. Sorry, Alok, can you make it the host again, please? Sorry.
Yeah. But I don't, 1 second, I don't see you now. 1 second.
I'm really hoping it doesn't disconnect again.
Suvrat, I'm not seeing. I saw it.
I'm here, no?
Yeah. Okay, you are a co-host. See if you can.
The host again. Okay.
Yeah.
Okay, excellent.
Yeah.
Okay, fine. Okay, sorry. So sorry for the interruptions. Apologies for the technical problem. So what I wanted to say was, in a theory of gravity, it's often unnatural to discuss algebras corresponding to local bulk regions. However, it's still possible to discuss asymptotic algebras. And the reason for this is that asymptotically, we often hold the geometry fixed even in a theory of gravity. So for instance, when we discuss ADS, what we really mean is that we might have, something happening in the bulk.
So sorry, there is a question in chat. Do you want to take the chat questions in the end or?
No, I can take them now. I'm not able to see.
I can just read it. It's by Krishna. That what about recent works of Witten et al. Who try to give a description of local observable algebras in this static patch?
Yeah, maybe we'll discuss this at the end of the lecture tomorrow. So, roughly the way these things work is you try and introduce an observer. Okay? And then in the presence of an observer, you can try and discuss, some observables which are addressed with respect to the observer. Okay? So we will discuss this kind of an asymptotic construction when we go on later. So maybe, tomorrow, in tomorrow's lecture, I'll discuss a little bit about how, you can make sense of local observables when you introduce an observer, or make some sense of local observables within some approximation. Right now, I just want to discuss the simplest thing, and I want to explain why it is that asymptotic algebras are simpler to discuss than algebras associated to regions, which we can do, but we'll work down to it maybe by tomorrow. Okay. Thank you. So asymptotic algebras make sense, and still make sense. And the reason they make sense is, when we discuss something that's happening in ADS CFT, the kind of picture we have is that there's some mess in the bulk, right? But at infinity, we believe, the way we define the theory of gravity is that we insist that at infinity, the metric goes to the ADS metric, right? And then it could have other subleading terms. But what this means, what this part means, is that we are insisting that the asymptotics is held fixed. Okay? And that's really important. Okay? It's really important that we insist that the asymptotics is held fixed. Similarly, when we think of flat space, we think of flat space, and when we draw this kind of a Penrose diagram, what we mean is that the asymptotics are held fixed. So these regions are the asymptotic boundaries. And what we want is that, as you go to infinity, then the metric should stop fluctuating. And at infinity, the metric should be that of flat space. Okay, so this is what we mean by asymptotically flat space. Okay. So it's important that, even in the theory of gravity, it is much simpler to discuss asymptotic algebras because asymptotically, the metric doesn't fluctuate. Okay? And that's how we define the theory of quantum gravity. In fact, when you do path integrals in quantum gravity, that's once again the way we work. The way we work is we fix the asymptotic geometry, and then we allow the bulk to do whatever it's going to do. And so that's why, the discussion that I'll have now will be a discussion of asymptotic algebras. And I'll explain how there are some interesting properties that we can derive that are associated to asymptotic algebras. And then, we'll go back and we'll discuss how, as the question asks, how one can make sense of things which are which exist locally in the bulk. But the point I want to emphasize in today's lecture is how even asymptotic algebras in ADS and in flat space have very different properties from the kinds of properties they would have in local quantum field theories. Okay, are there any questions about this very basic point?
Hi, Suvrat, a quick side question. Does your asymptopia necessarily have to be at infinity? Could you define gravity in sort of flat space by demanding that the metric take a given finite value, in the induced metric be a given finite induced metric at the boundary, gravity in a box? Is that allowed?
Well, I mean, people try to do that, but I don't know. I mean, I think it's hard to make this very precise. At least, I mean, it would be nice to do this, to say that, we put some boundary conditions at some point on some box and we fix the metric there. But this is something which, which is hard to do, and for obvious reasons, which is that, if you have a gravity wave that goes through, it causes the boundaries of the box to fluctuate, and then it's hard to define what one means by these boundaries. But I mean, people do try to do this, but and maybe it can be done. But once again, the infinity case is the simplest thing to do, and it would be very nice to do something more general and also discuss things at finite R.
Thank you.
Did you have something more precise in mind, Shiraz?
No, it was just this. I mean, your gravity wave, if you just specify the induced metric, then in the case of the gravity wave, you change your surface so that the induced metric is still that. So small fluctuations, I think classically small fluctuations you can deal with this way. I'm not sure about larger fluctuations.
Yeah, you're right. Perhaps small fluctuations you can deal with, and people do try to make sense of this. I mean, maybe one way to do this is to think of ADS and do some TT bar that allows you to flow inwards. And people have various ideas about how to do this. And once again, I'm not saying that this is something that can't be done, but I just want to discuss today asymptotic algebras because that's the simplest setup
Absolutely. I just wanted to understand whether being an infinity was going to be crucial to what you're doing, or
no, it will not be crucial. It's just where one can say the simplest things, where the simplest statements are possible, and so where a lot of these complications are things that one doesn't have to worry about. In fact, it would be nice to rephrase some of these statements at finite r, and to rephrase these statements in finite regions. But the moment one does that, one has to then deal with a lot of these complications and make things more precise. Whereas what I'm doing right now will just be very simple, because at infinity I don't have to deal with these complications. So it would be nice to move away, but it's not totally trivial to move away from this. Okay, are there any other questions about this, sir?
Yeah, Suvrat, there's a question in the chat. I think it's related to Shiraz's question. Wouldn't that give mass to the gravitons? I guess related to the Shiraz's finite boundary setup, maybe.
Wouldn't that give mass to the graviton? Sorry, there's a certain phenomena which occurs here, and the phenomena which occurs is that sometimes when people take ADS and they couple it to a bath. So maybe this is what. Let me just read the question. Wouldn't that give mass to the? Yeah. So maybe the phenomena that Mrityunjay is referring to is that if you take ADS and you couple it to a bath, then in higher dimensions, I don't know about how this works in 2 dimensions. Porati did a one loop calculation that showed that if you had leaky boundary conditions here, so the way people couple ADS to a bath is by means of transparent boundary conditions. Right? And if you have leaky boundary conditions here and you compute the one loop correction to the graviton self energy, then this is a calculation that Porati did. Then you find that the graviton in the bulk picks up a mass. But this is not okay. So that's some other issue, and maybe again we'll discuss a little bit of it tomorrow. But my impression was, Shiraz was discussing some setup which was, well, okay, it's not clear to me how one could do gravity in some finite region, or whether that necessarily involves something similar to this, where one also changes the bulk graviton theory and gives it a mass by putting some boundary conditions at some point. I don't know. Did you have something more precise in mind, Mrityunjay? I mean, this is the precise computation that I know about. Oof.
No, he's saying go ahead, Suvrat. He just said thanks. Yeah, I think it's all this.
This is again got disconnected. I'm only getting like 10 minutes
okay,
at a time.
Okay.
Oof. Guys, maybe should I take? I'm wondering if I should take a 5-minute break and call the IT people, so I can get more than 10 minutes, because it only, I don't know why it lets me connect only for like 10 minutes at a time.
Yeah. So we can. Okay, so we should just.
Well, okay. Let me try once more, please. I'm
okay,
really sorry about this tech issues and. Okay, the other alternative is maybe I can switch on a hotspot on my phone and just connect to that. Maybe that will work better actually. Then 1 second. Let me do that. Sorry, that will at least not get disconnected. Okay, let me do that. I think it will last for 2 hours. Sorry, guys, ICTS doesn't recognize me obviously anymore. maybe it's a hint that my network access has been turned off. This is how in corporate jobs you're told to you get the hint that 66402. Okay, hopefully this will work. This is
I just
please make me a co-host again. I have to apologize again for this. Yeah.
Yeah, you are a co-host.
I'm a co-host now. Okay,
Yeah.
thanks. Okay, good. So let me now say a little bit more about how these algebras work. Okay, so imagine in ADS, we have some field of. Let's just start with the simplest case. So imagine we have a field. And this is associated to some operator of dimension delta. So this field, if we denote as having some functions, depending on some phi, t, and r, phi of some time, of some radial coordinate, and of some coordinate in the sphere, then you can think of taking this field to infinity. And this defines for you some operator on the boundary. Okay? Now, this is really the boundary limit of a bulk operator. So just from the bulk, without at any point saying the words ADS CFT, or without, talking about a dual CFT, we could have defined an algebra of operators that lives on the boundary. And this algebra of operators just corresponds to products of these kinds of boundary operators and their linear combinations. Okay? So I would have defined some boundary algebra which just consists of things like this. And so on. Okay. So this is the simplest kind of asymptotic algebra that one can define. And it's something that's defined on the entire boundary. Similarly, yeah.
So, I mean, isn't this boundary value a source of the operator rather than the operator itself?
This boundary value is not the source of an operator. Sometimes one thinks of a source of an operator. No, this boundary, when you turn on a, so this is the normalizable mode of the field. Notice what's happening here. Let's say you had a field which was massless, then this delta would be D, and this is picking up the subleading term in the field. So the source that you're talking about would be, when you change the boundary conditions, okay, and you turn on a source. So that's something that corresponds to a non-normalizable mode. There's no source here. Okay? So in everything that I talk about, this is in fact an important point. Okay? So there are, we will not discuss at any point sources. Turning on sources on the boundary. And that's kind of, it goes along with the philosophy I mentioned earlier, which is that, you have some asymptotic algebra and you have some infinity, and at infinity, you don't do anything. You don't try to perturb what's happening at infinity. So you don't turn on sources at some finite value and keep them on or anything like that. Okay. So I hope this is clear. So these are really normalizable fluctuations.
Hi, Suvrat. Can I ask you a question?
Yeah, sure.
Yeah, so it's probably a technical point. If you could go back to the previous slide.
This one, yes.
Yeah, so it seems that your operators are local on the sphere, but I presume that the omega should be. I mean, you have to work in terms of spherical harmonics, right? Because otherwise, delta depends on the particular partial wave. So therefore,
delta doesn't depend on the partial wave. Delta is just delta for the field.
Delta will depend on the L.
No. Delta just depends on M. It's just delta into delta minus D is M. So delta is just D by 2 plus square root of D by 2 squared plus M squared. This delta is just.
Delta of the primary field.
Yeah, so maybe what you're thinking of is that the energy of the state that is produced does indeed depend on the partial wave and other harmonics.
Yeah.
But this is just the dimension of the operator, and this is indeed something you can define which is local on the sphere. You don't need to work in spherical harmonics. Later, I will smear things, but all the spherical harmonics have the same fall off. I mean, the fall off doesn't depend on spherical harmonics.
Okay, thank you. Thanks.
Yeah, because you have local operators on the boundary. Right? So local operators just to pick up the subleading term. That's local. Okay, good. So very good. So and the same way, at null infinity, you have fields that it's convenient to introduce a retarded coordinate. And this retarded time coordinate is just t minus r. Okay, so this is just what we would think of as t minus r. And it runs from minus infinity here to plus infinity here. Okay. And so it's convenient to think of null infinity in terms of this retarded time. And similarly, we can think of past null infinity in terms of an advanced time in exactly the same way. Okay. Now, the asymptotic structure of flat space is in fact more intricate than the asymptotic structure of ADS. And that's because, null infinity doesn't really provide a home for all boundary limits of bulk operators. Okay. However, if one thinks of massless fields, focuses on massless fields, then I plus or I minus provide a good home for boundary limits of bulk operators. Okay. So in fact, the simplest case to discuss is the case where you have d equal to 4. And then if you have a massless field in the bulk, a scalar field, then this field as a function of u, r, and omega goes to O of u omega by r. There's some 1 over r fall off. And once again, if you strip off the 1 over r fall off, you can pick up this boundary operator, this one. So this is once again my boundary operator.
So there is a raised hand, sorry, by Mrityunjay. Mrityunjay, you can just unmute and ask.
Yeah. Actually, I can't see the chat while I'm this.
Yeah, no. Chat. There is a raised hand. So yeah.
Go on, Mrityunjay. Yeah. Hello. I can't hear. Mrityunjay saying something or?
Mrityunjay, we can't hear you. Maybe you can just type in the chat if there's also. I can ask Suvrat.
I think there is also a question in the chat in the meantime, maybe.
Yeah, are we allowed arbitrary products of operators? Yeah, we are allowed arbitrary products of operators right now. So we are not putting any limit right now. And in fact, that's one reason why, there was a question earlier about associating operators to local regions R, which, as I said, we'll try and discuss tomorrow. When you associate operators to local regions R, you have to be very careful about whether you really get an algebra or not. Okay? And that's because, it sometimes happens that when you associate operators to local regions R, then you have to be careful about, what is the size of the products that you can take. Here, because we are at infinity, it really makes sense to talk of an algebra. Okay, so we are allowed, the answer to the question is that we are allowed arbitrary products of operators.
Yeah, am I audible now?
Yeah, you're audible now. Go on, please. Yeah.
When you're defining this algebra on the boundary A,
yes,
you are taking only the operators O, which are decided by the mass of the field that you have taken in the bulk.
Correct.
So the whole algebra is kind of built up from the one operator, right?
No, the full, so there might be different fields. So the assumption in this whole story is that if you go to asymptotic infinity, then the language of quantum field theory makes sense. For instance, even when you're doing string theory, we believe that a S matrix makes sense. So you go asymptotically far away, and there the language of quantum field theory makes sense. So it makes sense to speak of fields with different masses. And for the field of every mass, for instance, in ADS, corresponding to every such asymptotic field, you can define some boundary operator.
If I take some other field, phi,
then you would have a different, So if you had a different field phi, you'd have a different dimension. So you define r to the delta times phi tilde. This might be delta tilde. And this would give you O tilde, T omega. like I wrote, this is what I wrote right now. I just wrote a different limit with r to the different dimension corresponding to a different mass gives you a different operator on the boundary.
So if I want to study some observables in the asymptotic limit, then I'll have to always consider the corresponding operator and build up the algebra for that.
Sorry, now I'm not able to hear. If you want to study what?
The algebra in the asymptotic limit, then I'll always have to choose the operators corresponding to the bulk field that I'm interested in.
No, the boundary algebra is that you take the set of all of these fields and you take all of these you take all of these boundary operators, and that gives you a boundary algebra. In fact, I'll discuss in a minute what happens if you try to restrict to some set, but go on, please. Yeah.
So I mean, if I have some delta tilde operator, then that could also be put in this A video.
Yes, it would be put in the A. Thank you. Yes.
Okay.
Indeed,
Thanks.
it would be put in the A. Yeah, thank you very much for the question. Yeah, so what I've written here is a schematic representation of A. Of course, if you had other operators, other boundary operators, you would include them in A. Okay, so A is, it's not that this O is the only algebra, or I want to focus on the algebra corresponding to a single field. In particular, as we'll discuss later, when we have gravity, there'll be the metric, and it's important that you include the metric, okay, in the story.
So Suvrat, there's a question in the chat. Does this algebra also include boundary limit of the graviton in the bulk? If so, what would that become in the boundary? I guess you just answered it.
Yeah, exactly. It includes the boundary limit of the graviton in the bulk, right? So in the bulk, let me just write this down precisely. Let me do this in flat space. In flat space, when you write down the metric, it looks like this, okay? I'm sorry, my R and my gammas all look the same. One is R, one is gamma. Okay, and then these are the subleading terms in the metric, okay, and these terms are important. Okay. This term is called the Bondi mass, so it's called a mass aspect, okay? And this term is called the shear. Okay? And these terms do indeed become operators, or we will think of them as living on null infinity. Okay, so this is the bulk metric, and as I said, we insist that the metric at leading order becomes that of flat space, and then it has some subleading terms, and these are the subleading terms, and these subleading terms we will think of as living on the algebra of null infinity. Okay, so that's the answer to the question. Does that answer the question?
I think so.
Okay.
We already. Okay. So there's another question. Sorry, Suvrat. How does this definition of boundary operator differ from the one that involves bulk to boundary propagator?
That involves the bulk to boundary propagator. Usually, sometimes if you want, here I'm just trying to take the boundary limit of a bulk operator. Maybe if you said, there are different setups in which you use bulk to boundary propagators, right? If you wanted to compute the correlation function of some of these boundary operators, then you would need to use bulk to boundary operators to propagate their effect into the bulk and so on. But we are not doing that here. So there is no, usually people don't define a boundary operator using a bulk to boundary propagator. That's something you would use if you wanted to compute correlators of this algebra in ADS. But here we are just trying to understand some other properties of the algebra. So we won't need to go back into the bulk. Okay, I hope that answers the question. Okay, good. So now, I want to say something about the Hilbert space. Okay. Now this algebra has, let's assume, okay, and we'll assume in whatever we are doing, there's a vacuum. And we'll call this vacuum state omega. In fact, in four-dimensional flat space, we have to be careful about this because the vacuum is, not unique. And in fact, there are all these, super translation sectors that you have to be careful of. In these lectures, I thought, I would avoid some of that complication. And I'll just assume that there is a unique vacuum, and, which is true both in ADS and also in, when I discuss flat space, I'll also assume that we're talking about one vacuum. For those of you who want to be very careful, I'm happy to discuss a little bit more how you can, deal with the fact that they're degenerate vacua in flat space, but that's kind of distracts us from the main part of the story. Okay. So if you give me a vacuum omega, then the Hilbert space is generated by acting with this boundary algebra on omega. Okay. And this is kind of clear, by the way, if you think of how we set up scattering, how we set up the scattering matrix in flat space, and that is that the out space is generated by thinking of all of these asymptotic operators that live at null infinity, okay, and exciting the vacuum with it. It's also true in ADS that if you take this set of boundary operators and you act on the vacuum, then you generate the full Hilbert space. Now, there's a slight subtlety here, and so I want to discuss that. It's also related to this question that was asked earlier about, what are the precise boundary operators that you include in the algebra. Okay? So what I want to say right now is that there's this Hilbert space that I was just discussing, which, as I said, came by acting with these operators. On the vacuum. Now, the point I want to make here is that this is a super selection sector. In that it evolves to itself under Hamiltonian evolution. So, even if there are subtleties about what operators you included in this definition of the boundary algebra, did you include fields of all masses? What if there are some operators that don't have some good definition as free fields, even at infinity? The point is that this Hilbert space is still good enough because it evolves to itself under Hamiltonian evolution. And the reason for that is very simple, and that is that under Hamiltonian evolution, if you take a state of this kind and you evolve it goes to this. But this operator was an element of your algebra, and this operator was also an element of your algebra. Okay. Therefore, this state was an element of your Hilbert space, and this state is also an element of your Hilbert space. Okay. So, whatever this Hilbert space is, this Hilbert space is a good Hilbert space to work with, because just by doing evolution, you never evolve out of this Hilbert space. Okay. This is also true, by the way, the same argument holds at null infinity, which is that there's some Hilbert space, and just by doing evolution on null infinity, you don't go outside that Hilbert space. Okay. Okay. Is there any question about this?
So there was one question in the chat earlier. How does the shear term appear in the boundary algebra?
How does the shear term appear in the boundary algebra? So usually, we think of the metric as being the derivative of the shear with respect to the retarded time. But the shear term itself you can think of as a field that appears in the boundary algebra, or you can think of this Bondi news.
Okay, and there was just one more question. Algebra contains arbitrary product of operators.
Yes. The Hilbert space is infinite dimensional. For sure, the Hilbert space is infinite dimensional. Remember, by the way, the Hilbert space of a simple harmonic oscillator is infinite dimensional. So the Hilbert space is definitely infinite dimensional. Okay, good. So now I want to prove. This is the Hilbert space that we'll work in, which is so far I defined a boundary algebra, and I said there's a Hilbert space that you get by acting on the vacuum with this boundary algebra. Now I want to explain the first somewhat non-trivial result, which is how you can squeeze. Well, okay. Let me first define an algebra of a band, and then I'll say something else. Now, so far I was talking about the asymptotic algebra, which had to do with the algebra of operators everywhere on null infinity. But now let me think of an algebra that lives on some part of the asymptotic boundary. Okay? So maybe like this part of the asymptotic boundary. Similarly, in flat
Can I
space,
ask a question?
yeah, go on, please. Yeah.
In the case of the flat space,
Yes.
how is this Hilbert space that is defined by acting on with this algebra different from the usual Fock space that we have?
No, it's
the
usual Fock space. It's the usual Fock space.
So then, if I have a naive one particle state, then the function that I need to smear a field operator with would be something like an exponential, right? Is
e to the I omega u, yeah, to get a one particle state of definite momentum, correct?
Yes, but wouldn't that violate what conditions one may have on these smearing functions, like finiteness of the mod f square integral should be less than.
I mean, that's a question of whether you want your one particle state to be normalizable or not. If you take a momentum eigenstate, it's not normalizable. If you want to create a normalizable state, you take O of u omega and normal, So the question is, if you look at, so you're talking about flat space, right? Because I'm trying to discuss both together.
Yes, flat space, yes.
So this is a one particle state. And this one particle state, is normalizable if F has the nice properties. If you want to create a one particle state, which is a momentum eigenstate, then you have to take F to be e to the I omega u. But that's not a normalizable state. That's delta function normalizable. You could take F to be a nice Gaussian, you'd get a nice state, one particle state.
I see. Okay. When you define the Hilbert space, it also requires the definition of what F's you allow.
I wasn't being very careful about that, but indeed, you're right. If you want to look at normalizable states, that'll give you some set of, you have to pick some elements of the algebra. You're right. So, you're right that the Hilbert space I got included also these, yeah, okay. So thank you. Maybe this goes back to the comment I made in the beginning. For instance, this algebra I defined was really the algebra of products of pointwise defined operators. And that will not give rise to states which are normalizable. And so you're right, you need to smear these things and be a little more careful to get normalizable states.
Okay, thanks.
Hi, can I make a comment about this point about Hilbert space and operators that are involved?
Yeah, sure.
If you're working with bounded operators, then it in some sense doesn't matter. But if you're working with unbounded operators, then it does matter which unbounded operators you're working with. And then you have to be more careful about how you go around defining the action of these unbounded operators on your Hilbert space. And it goes back to your example of the momentum operator.
Yeah.
The momentum operator is an unbounded operator. Yes. And you can easily think of wave functions that when you act, normalizable wave functions that when you act on by the momentum operator are kicked out of the Hilbert space. They're no longer normalizable.
I agree with all of this, and indeed that you're right that one needs to be more careful about.
But to come back to what I was saying is that if you're working with bounded operators, then this is much less of an issue.
Yeah, sure. So once again, I have to apologize a little bit because I will be a little sloppy about this. But I think that everything I'm saying you could probably rephrase by speaking strictly in terms of bounded operators. And I don't think there's a problem if one discusses things strictly in terms of bounded operators. In particular, as you said, the Hilbert space you could produce by thinking of the set of all bounded operators within this algebra and acting on the vacuum, and that would also generate the Hilbert space. So you could really think in terms of von Neumann algebras. In my presentation, I'm not being that precise, but I don't think there's anything essential that's lost by this lack of precision. But one could indeed do this. Okay. So now I want to discuss a little bit the algebra of a band. Okay? And when I want to, so what I want to discuss here is that so far I discussed the algebra, the asymptotic algebra that corresponded to operators that live everywhere on null infinity. But now I want to restrict operators to some part of null infinity or some part of the asymptotic ADS boundary. Okay. So in particular, I want to define an algebra that I'll call A epsilon, both in ADS and in flat space. And in ADS, this algebra corresponds to the same kinds of things, the same kinds of products But now with an additional provision, which is that this Ti only lives in the time band 0 to epsilon. Similarly, this is in EDS. In flat space, this algebra again consists of these products. But with the provision that this U coordinate, let me write here, is in some band from -infinity to -1 over epsilon. So in fact, in flat space, I'm still talking about some semi-infinite interval, even though it looks small on the Penrose diagram. But in ADS, I'm really talking about some small region on the boundary. Okay, so this is the algebra of a band that I'll denote in both cases by A epsilon. So this is clearly a sub-algebra of the full algebra. So in particular, in an LQFT, not in a theory of gravity, as I'll explain, if you take this algebra of a band, then there are many elements of the full algebra that commute with this algebra. So for instance, if you take an unitary operator U here, then this in an LQFT, a unitary near the bulk, near the center, it commutes with all elements of A epsilon. So this unitary really belongs to the commutant of this algebra. Okay, so this algebra has a commutant, and this commutant, in fact, you can obtain by roughly by thinking of the entanglement wedge of this band, or in some in the absence of gravity, just this causal wedge, these triangles that I've drawn, and thinking of the complement of that region. Okay, and so in an LQFT, this algebra is clearly a sub-algebra of the full algebra. The same thing, by the way, is true if you think of null infinity. Okay, that this algebra that we have here is really a sub-algebra of the full algebra.
Okay. Hi, Suvrat. Can I ask one question?
Yeah, sure.
So if your algebra includes Hamiltonian, then isn't that true that Hamiltonian can take this operator out of this region?
Yeah. So that's indeed what I want to discuss. So in a local quantum field theory, the algebra does not include the Hamiltonian because the Hamiltonian is not a boundary term. So it is true that in a theory of gravity, and that's one of the points I'd like to make in the next 15 minutes, is that because when you include the Hamiltonian, and we'll be a little more precise about how we include that. Indeed, this algebra becomes the full algebra, but in a local quantum field theory, the Hamiltonian is not an element of this time band algebra. Okay.
Yeah. Otherwise, it should be the full algebra, right? The algebra in this small region should be the algebra of the full null slice, right?
Yeah, it is the algebra. So, what I want to contrast here is how things change when in the absence of gravity and in the presence of gravity. Okay. So in the absence of gravity, the Hamiltonian is not an element of the algebra. And as I'll emphasize, in the presence of gravity, the Hamiltonian is an element of the algebra.
Okay. Thanks.
And that makes a difference to how, yeah.
So there are two questions. One is, if instead of working with compact dimension omega, if you work with a non-compact dimension X, does this Hilbert space?
Compact dimension omega. This omega I'm just thinking of as the sphere coordinate. This is just the coordinate along the boundary. It's this coordinate. This is omega. There's also an omega that you can draw in flat space. It's just the coordinate that goes around. That's because I'm drawing these diagrams which are flattened, and so omega is just the coordinate of the sphere.
I hope that
there's no reason to consider. No, you could consider other operators as well. Sure. You don't have to consider unitary operators only.
Okay.
Yeah. Other operators will come as well. Yeah. Okay, good. So now I want to explain. I want to make the first non-trivial statement, and this is also true in a local quantum field theory. Okay? If you think of the space obtained by acting with A epsilon on omega, is dense in the full Hilbert space. Okay. This might be slightly surprising because, initially I defined the Hilbert space as acting with the full algebra on the vacuum. Okay. Now I want to say, well, if you just acted with this small subalgebra on the vacuum, that is still enough to generate the full Hilbert space. Okay? Let me explain why that is the case. So the proof goes by contradiction. Imagine, so let's actually first think just of single particle states, okay? So restrict to states. They don't have to be single particle, but just obtained by acting with a single operator on the vacuum. Okay, and then I'll explain how it generalizes. Okay. There are two omegas here. One omega is the sphere, one omega is the vacuum. I hope that doesn't cause confusion. Okay. Okay. So now I want to say that, even if you restrict, so the claim is that even if we restrict F to have support in 0 to epsilon, this is sufficient to obtain all states. In fact, the precise statement is that it's sufficient to arbitrarily approximate any state. Okay. Okay. So let me prove this. So the proof goes by contradiction. Imagine, say there was some state psi, that cannot be obtained in this manner. In that, however hard you try to approximate it by using these functions which have support in the interval 0 to epsilon, you can't get the state psi. If that's the case, there must be some part of the state psi that's in fact orthogonal to all these states which are obtained by acting with these operators in this band from 0 to epsilon on the vacuum. Okay. So there must be some state psi prime with the property that psi prime is in fact orthogonal to all these states. And that's the reason all F with support in 0 epsilon. And that's the reason, because this psi prime is somehow an element of psi or has psi has some component which is parallel to psi prime. That's the reason we are not able to approximate psi arbitrarily well by acting with these functions of this compact support. Okay. However, this implies that psi prime okay. This means that psi prime must in fact, the matrix element of these operators O, when t takes the value between 0 to omega, between the vacuum and the state psi prime must be 0. However, now notice that this matrix element you can write in this way by inserting a complete set of energy eigenstates. Okay. So these are some coefficients. These are some numbers. They are whatever they are. Okay. These are some numbers. Okay. But interestingly, we pull out a factor of e to the IET here. Okay. By looking at this, you see that this matrix element is an analytic function or is analytic when t is extended in the upper half plane. And the reason for that is that this E only runs over energies which are bounded below, which is a property that we expect to hold in any good, well-defined theory. And as a result, you see that this matrix element is analytic whenever T is extended in the upper half plane. Is that clear? Because, whenever T is extended in the upper half plane, if you take T to T plus IZ, then this factor combines here and gives you some factor that dies off at larger and larger energies. So if this initial matrix element was convergent, if the sum over energies was convergent, after adding this factor, it only improves the convergence of the sum. And therefore, if the original matrix element is well defined, then, after and doesn't have any singularities, then even after you make this extension, it's clear, right? It doesn't have any singularities. Okay, good. But now, by assumption, equal to 0 for T in this region. But we know that this matrix element is analytic in the upper half plane. Therefore, a standard result from complex analysis tells us that this matrix element must be 0 for all real T. But now, we are in trouble because we assume was of the form for some, for some smearing function G, right? So it cannot be the case that it's orthogonal to O of T omega acting on the vacuum for all times. Okay? And therefore, we've reached a contradiction with the fact that psi itself was produced by the action of a single field acting on the vacuum. And it was orthogonal to the action of the single field acting on the vacuum in this time band. This is a trivial example of what's called the Riesz-Leader theorem. The Riesz-Leader theorem, which is proved in local quantum field theory, is a more involved theorem that sometimes has to do with the algebras of local regions. Here, we are just thinking of the asymptotic algebras in a time band. And so it's a very simple theorem. It only requires the positivity of energy. In general, the Riesz-Leader theorem requires something a little more elaborate called the spectrum condition. But we don't need to invoke that here. As long as we have the positivity of energy, we can see that the action of the algebra on the small time band on the vacuum is sufficient to approximate any state in the full Hilbert space. By the way, the proof I gave here was a proof for the action of elements of the algebra that had a single field. But the same kind of proof also works if you think of more complicated products. So for instance, if you now think of, let psi be a like n particles or n field operators, then once again, the claim is that you can restrict the support of the smearing function to all the times in the range 0 to epsilon. Okay? And running through the same arguments, what we need to examine is this kind of matrix element. And you insert complete sets of energy states everywhere in the middle. Okay. And when you do that, you'll now find that what you'll find will be some terms, if you just look at the T dependence, that look like, sorry. So this arrow just means I'm looking at the t dependence, and you can see that this t dependence will all be of this kind. Is this clear, or am I going too fast here? Because I suddenly stopped getting questions.
As there is a raised hand actually, Suvrat.
Oh, go on, please.
Yeah. So in the argument that you used to show that this proof by contradiction, it required the resolution of identity by these energy eigenstates. So and these are
it required a resolution of the identity using energy eigenstate. Then I couldn't hear anything. Sorry.
So I was but they're semi-infinite. They're bounded below. Right?
Yes,
that was the
they're
requirement
bounded below. They're semi-infinite.
to show
Correct.
this, to prove this.
Correct.
So would that place a constraint on the Hilbert space that one? So I wouldn't be allowed arbitrary pointwise. Would it put a constraint on the smearing function that I used for my Hilbert space? Like, are they complete in the most general Hilbert space I could construct, or
again, I'm not sure at what level
of
of
most general Hilbert space that I could construct.
Again, I'm not sure at what level of rigor you're asking this question. But if I take a state which was bounded, which had bounded norm, which was normalizable in the original Hilbert space, so I choose this G so that, or this G, so that this state psi is something which has finite norm, then I can find another function f so that I approximate this psi arbitrarily well, but that f has bounded support within the region 0 to epsilon.
I see. So it requires boundedness of the smearing function.
Not actually boundedness of the smearing function, boundedness of the state. It requires the state to have finite norm. I'm just restricting to Hilbert space states which have finite norm. That's slightly different from boundedness of the smearing function, because the norm is obtained by taking the smearing function and convoluting it with the 2-point function of the operator itself.
I see. Okay. Thanks.
Okay. So, once again, if you do this for this n particle state, you will find some dependence. What will happen? Yeah, you'll find some time dependence which looks like this. And if you define, some operators which look like Z1 equal to T1, Z2 equal to T2 minus T1, Z3 equal to T3 minus T2, okay, then the matrix element is analytic when the zi's are extended in the upper half plane by the same logic that we had previously. Okay. And therefore, once again, there's a theorem in complex analysis. It's called the edge of the wedge theorem, which is just a more elaborate version of what we just said right now in 1 dimensions. And there's a nice proof in Witten's lecture notes on this if you want to see how this theorem goes. The edge of the wedge theorem tells us that, if this vanishes when, tells us that if the matrix element vanishes for all ti in 0 to epsilon, it vanishes for all ti. Okay, so once again, even for states produced by the action of n of these operators in the vacuum, you can show that if you take the squeezed algebra, that is sufficient to generate the full Hilbert space. Okay, are there any questions about this? So far, in fact, we haven't even said anything about gravity. Now I want to say a few things about gravity, but so far what I've said is just true in quantum field theory.
Yes, Suvrat. You proved that this A epsilon on the Hilbert space, it produces the full Hilbert space, but in the beginning you said that it is dense in the full Hilbert.
Okay, thank you. Indeed, you're right. So indeed, the precise result is that it's dense in the full Hilbert space, and that any state in the full Hilbert space can be approximated arbitrarily well by an element of this. Because you see, what I needed to do to make the proof was I needed to say that imagine there was some finite residual. Imagine there was some state psi which could not be obtained in this manner. Okay, then there must have been some state psi prime which is orthogonal. That's because psi has some finite residual, and that's why I'm not being able to approximate it arbitrarily well. So what I really proved is that you can never have a finite residual. And so you're right. The precise statement is that, the operator can be approximated arbitrarily well. Sorry, the state can be approximated arbitrarily well.
Okay, thank you.
Okay, good. Are there any other questions about this, sir?
Nothing in the chat, Suvrat.
Nothing in the chat, right? Okay, good. So now let me say something about gravity. Okay. So what is special about so far all our statements apply to LQFTs and to gravity. So there's nothing that we said that is not true in a field theory, okay? And there's nothing that we said that's not true in gravity. Of course, in assuming that the statement applies in gravity, I'm assuming that in the full theory of gravity, the energy is still bounded below, which we believe should be true in a general, which we believe should be true in some well-defined theory of gravity. Okay, so now what is special about gravity? Okay. So what is special about gravity is that the Hamiltonian is a boundary term. Okay. Let me give you a few perspectives on this, okay, for those of you who are not familiar with this. You see, this is actually a very physical statement from one perspective. And this is just the Gauss law. The Gauss law tells us that, if we go off, if we, have some energy here, and we want to measure how much energy there is, then we don't actually have to go and measure the local energy density in a theory of gravity. It's sufficient to measure the gravitational field outside here on a Gaussian surface. Okay? And therefore, the Gauss law tells us that, the energy can be measured from infinity. In fact, in a theory of, in general relativity, those of you who've, the only good definition of energy comes by looking at, the energy at infinity. It comes from the ADM Hamiltonian, which is defined at infinity. Okay? And the reason, so in fact, in GR, the good definition of infinity, the good definition of energy is at infinity. And this is once again, for the same kinds of reasons that we discussed, which is that in the bulk, all sorts of things might be happening, the metric might be fluctuating. And therefore, when we try to define the energy, we really define the energy by, going out to infinity and by looking at the subleading fall off of the metric. And that's something that we check by making sure it works in the linearized theory. But then we say this is the definition of the energy. So the fact that the Hamiltonian is a boundary term is true. It's true in the Newtonian theory. It's also true in general relativity. Okay. Let me say this in another way for those of you who are more familiar with ADS-CFT. Okay. You see, in ADS-CFT, we have a metric operator in the bulk. And one of the the boundary value of the metric operator, if you take the metric operator, you scale it with the right power of R, this gives you the stress tensor on the boundary. And these i's and j's are boundary coordinates. So in particular, one of the components of the stress tensor that you get by considering the boundary limit of G00 is just T00. And if you integrate T00 on the sphere, you get the Hamiltonian. So even in examples where we understand how quantum gravity works, the Hamiltonian is indeed a boundary term. Okay, here's a third perspective, which is from, all these things that I'm saying are related. So if you think of canonically quantized gravity, then what you need, and you think of states in canonically quantized gravity, then what you need to ensure is that, if you think of some state psi in canonically quantized gravity, then the state psi must be invariant under small diffeomorphisms. Okay. And small diffs are diffs that might move you locally up and down in time. Might move you some, might change a slice to something of this kind. And that tells you that H bulk on psi is equal to 0. And in fact, this is called the Hamiltonian constraint. Okay. And so the only part of the Hamiltonian that survives is the boundary term. Okay, so I give you 3 quick arguments to explain why in a theory of gravity, unlike in any other theory, the Hamiltonian is a boundary term.
Sorry, Suvrat, can you just explain this perspective 2? I think this
perspective 2 is just from ADS-CFT. Yeah.
Can you just tell it once again? Like
I was just saying that, if you think of the boundary metric, if you think of the bulk metric, then this goes to the boundary stress tensor, right? And the Hamiltonian of the boundary theory is the integral of the 0,0 component of the stress tensor. And therefore, that tells you that the integral of the 0,0 component of the bulk metric is the Hamiltonian of the theory. So in ADS-CFT also, you see that the Hamiltonian is some element of this boundary algebra as we've been defining it.
So integral of G00 gives you the bulk Hamiltonian, or
it gives you the full Hamiltonian.
Hamiltonian.
Yeah. More precisely, you have to be a little careful. You have to take Gij. You have to look at the subleading part. That's why I wrote an arrow. Okay, so you have to subtract off the pure ADS part, and you have to look at the subleading part. And then indeed, once you take that subleading part and you scale it up with a factor of R squared, you get the Hamiltonian. You get the full Hamiltonian.
Okay, thanks.
Okay, thank you. Are there any other questions about this? Okay. Now I want to explain why this very simple property of gravity creates a rather significant difference between the way algebras behave in local quantum field theory and the way algebras behave in a theory of gravity. Okay. So in particular, I'll assume, the Hamiltonian is a boundary term. And remember, I said earlier in this discussion that we had a vacuum on top of which we were building states. If you measure the Hamiltonian, and in fact, for those who like bounded operators, what you're really supposed to get, what the rules of quantum mechanics tell you, is that there's a probability of getting a certain energy, and the probability with which you get a certain energy is given by the expectation value of the projector onto that energy. So in particular, one of the elements of the algebra, which is the projector on the vacuum, is also an element of the boundary algebra in gravity. And this is simply because the Hamiltonian is an element of the boundary algebra. So in fact, one of the bounded functions you can construct from the Hamiltonian is the projector on the vacuum. But this is a very basic thing. It's very physical because it's just telling you, if you measure the energy, what's the probability you will get 0. Okay. So now I want to say, as a consequence of this, in gravity, any element of this big algebra of the asymptotic algebra A which was this algebra I defined at the beginning, can be approximated arbitrarily well by an element of A epsilon. Which was this algebra that I had in the small band. Okay. So this might be this is now a statement which is very different from the kind of, so earlier I emphasized that this small band algebra was just a sub-algebra of the full theory. But now I want to say that it's not a sub-algebra in a theory of gravity. Once you add on the projector and the vacuum, which is true from these different perspectives, then in fact, you can arbitrarily approximate any operator in the theory. Okay, you can approximate it arbitrarily well. So now I want to give you a proof of this statement. Okay. So let Q be an arbitrary operator. Okay. And let's expand it out in our favorite basis. There's some choice of basis. Okay. It's just some basis. Okay. Now, from the result we proved earlier, there is some element of the algebra A epsilon whose action on the vacuum gives you each element of this basis n, right? Of this basis that we have. This so far is also true in QFT. What I've written so far. Is this clear why this is true in QFT? This just follows from the result we proved earlier. And that's because you can generate all states by acting on the vacuum in a local quantum field theory. Okay? This doesn't negate the fact that all operators in the theory are not elements of A epsilon. Okay? It just tells us that, you can, if you like, even in local quantum field theory, you could write every operator in this form with this projector and the vacuum included sitting in the middle. Okay. Is this clear, or are there any questions about this, sir?
Nothing in the chat.
Okay.
So.
Can I ask
Okay,
you
good.
I think there are questions over it in the.
Hi. Maybe you can postpone it if it's a distraction, but so the time band algebra that you're considering, can you comment on the nature of the, like, if it's in a von Neumann algebra sense?
Yeah.
What is the nature of the algebra?
This is what I was saying earlier. If you made everything into bounded functions, then these would be von Neumann algebras. In a local quantum field theory, this would be some type 3 algebra, and here I'm going to say it would be a type 1 algebra. But I want to say that I want to stay away from a lot of this very formal classification, as I said at the beginning. But that's
so because I asked this because the kind of projectors that you are writing down, the NM projector,
yes,
would that be part of the algebra? Is what I was worried.
Would that be
part of the algebra?
Yeah, sure, for sure, they would be part of the algebra, right? They're nice bounded functions. The projector is a very nice function. So if you want to think of, be very rigorous and think of bounded functions, then the spectral projectors of the operator are surely part of the algebra, right?
Okay. Thanks. Yeah.
Yeah. So if so the projectors would are very nice bounded operators. So there's no problem including them in the algebra. Okay. But in gravity, this guy that sits in the middle is also an element of the algebra, right? This is just a projector on the vacuum. Therefore, we have found that any operator Q with no restrictions, and this is now a linear combination of a product of 3 elements of A epsilon. And therefore, since the algebra is closed under products and linear combinations, we find that all operators Q, in fact, belong to this algebra. Okay. So this is the statement that the nature of the algebra changes very significantly in gravity as compared to a local quantum field theory, because one includes the projector and the vacuum. Okay. And the same argument that we just discussed holds both in ADS and in flat space. Okay. Okay, so this is a very surprising. It's a very surprising statement, and what I'll do in my lecture tomorrow is I'll explain some more of the physics of this statement. But I just go on.
Yeah. So earlier you said this projector is an element of the algebra or A epsilon, A sigma.
Thank you. The projector is an element both of A epsilon and of the algebra. Thank you for that question. You see, because the Hamiltonian is a boundary term. But see, A epsilon was defined in terms of my operators that lived in this time band, right? So the Hamiltonian you can define at any time. So it's an element of A, but it's also an element of A epsilon. Similarly, and maybe I should have been more clear about this in flat space. In flat space, my A epsilon was defined here. And in fact, the Hamiltonian is defined here. You know, in flat space, the Hamiltonian is defined, in fact, as the limit is u goes to minus infinity of the Bondi mass, okay, of one of these Bondi mass operators that we had. So indeed, the Hamiltonian is an element of A epsilon. It's also an element of A, of course, but it's an element of A epsilon.
Yes,
yeah.
Can you, sorry,
yeah. So Hamiltonian is an element of A epsilon. So does that make this projector also an element of A epsilon?
Yes, the projector is a function of the Hamiltonian. It's one of the spectral projectors of the Hamiltonian. So, you know, if the Hamiltonian is part of A epsilon, the projector you can think of as being a bounded function of H. So, you know, when you include an operator, you have to also include all of its spectral projectors in the algebra. Let me say it another way. In quantum mechanics, when you measure the operator, what quantum mechanics tells you is that you get various results, and the probability with which you get various results is proportional to the expectation values of these projectors. So the projectors are kind of very basic elements of the operator.
Okay, thanks.
Okay, are there any other questions about this? Okay, I want to say something. You know, from the point of view of ADS-CFT, this is kind of an obvious result. Okay, from.
Hi, Suvrat.
Yeah, hi.
Hi. Can you emphasize a little more as to why this difference crops up with theories with gravity, as opposed to local quantum field theories?
Because in a local quantum field theory, the projector and the vacuum is not an element of this asymptotic algebra, right? There is nothing that tells you that in a local quantum field theory, if you just take a local quantum field theory and look at the boundary limits of these bulk operators, there is no element of that algebra that can let you measure the energy. So it's because of the Gauss law, right? That's the physical way of saying this.
Okay. Thank you.
So there's a question in the chat. Why is it that the ground state projector is absent?
I think it's the same question that was asked right now. Right? Yeah. So from ADS-CFT, this result just seems trivial, right? This result is trivial. And that's because, you know, what are we saying? What we're saying is that you take this algebra here, this algebra of this time band. Just think of the boundary perspective, right? Because so from the boundary perspective, this is the algebra of the whole boundary for a time epsilon, right? So this is the algebra A epsilon is the algebra of the whole boundary and this is clearly complete, right? Because it's the algebra of the whole boundary. And not only at a single time, you don't even need a time band in ADS-CFT, you just need a time slice. And therefore, in ADS-CFT, this result is trivial. But we did not invoke ADS-CFT in proving this. So I think this gives us an understanding of why it is that gravitational theories are holographic. Because what we proved right now is that the full algebra of the theory lives at the boundary. So this tells us why gravitational theories are holographic. So it's true that if you assume, you know, ADS-CFT, this would be true, but we didn't invoke ADS-CFT in proving this. And I think this gives us an understanding of why it is that gravitational theories are holographic. Okay. Okay, so I see actually I'm already out of time. So in fact, let me just give you a preview of what I'll discuss tomorrow. And once again, since this is a diverse audience, if I was going too slowly, I'm happy to say other things. So what I wanted to discuss tomorrow is, just a little bit more of the physics of this result. Some low energy tests and black holes. And then I also wanted to discuss a little bit about the question that was asked in the beginning, which is how we can talk about observers and local algebras. I won't have something very precise to say, but I think there's some understanding we can have of that. And so I'll discuss that. And maybe if time permitting, today I discussed ADS and flat space. I'll discuss, I'll discuss perhaps DS. Okay. So that's my plan for the next lecture. I don't know how much I'll go through, but since I'm already out of time, let me stop here and see if there are any more questions.
Okay, so let's first thank Suvrat for a very nice lecture, and then we have if there are more questions. There were already many questions during the talk, but if there are more questions, please ask.
Oh, sorry, but maybe you'll touch it upon tomorrow as well. But you mentioned that in defining the local notion of the algebra, you always have to dress it with respect to some observer or some world line or something.
Yeah.
But there was a recent paper by Kyriakos and others who tried to dress it with respect to curvature invariance. Like they define a notion.
Sure, you can dress it with respect to some other. I mean, observer doesn't have to be a physical observer. You can have some other physical. You can have some, star or supernova. Any heavy state allows you to dress these algebras. So, observer doesn't have to be. Sorry, maybe I didn't understand the question. For sure, the observer can be any feature of the geometry. So if you have sufficiently heavy background, that provides an observer.
And what do you mean by sufficiently heavy background?
I'll try and make that a little bit more precise tomorrow, but roughly sufficiently heavy has to do with, an entropy density that's non-perturbative already. So, we'll have to try and make this a little bit more precise when we talk about local algebras, because these won't really be algebras. So we'll have to say, you can talk about some information that's confined to some local region that doesn't exist outside the region, provided you restrict yourself to some accuracy. So you'll have to say what that accuracy is. And depending on that, you'll have to say how heavy the observer is. Okay? So, one way to think about it is an ADS-CFT sufficiently heavy is anything of n or higher. If n is the ratio of the Planck scale to the ADS scale.
And one other question regarding the Hilbert space. So, the Hilbert space was constructed by acting with every element of the boundary observable algebra on the vacuum state, which is defined to be the lowest energy state of the Hamiltonian.
Correct.
Now, it's infinite dimensional, but I asked it previously as well, like it's not really separable, right? Because you can have arbitrary times. The timing is the operators, they are defined on a continuous time. So you don't have a notion of a separable Hilbert space anymore, right?
No, it is separable.
I'm not sure why you say it's not separable actually.
Because so for example, even the one particle states.
So Are you asking once again about smearing things? For instance, are you saying that I should smear things with some nice smearing functions?
No, just the way that you have written it. You have written it like a span of OT1, omega1, OT1, omega2, and so on, right?
So you're saying I should have written this?
I'm not saying anything about the smearing function, but is this a more precise definition of what you meant?
Yes. If I had a smearing function, it would be a more precise definition.
Okay.
It would then have, that we discussed this a little bit so that we have to have normalizable states. Yes.
Sure. Okay.
I mean, it's the same sense that normal QFT Fock space is separable.
I see. Right. Okay.
Yeah, hi, Suvrat. Can you actually go over the first perspective argument? I just missed it. Sorry.
On why the Hamiltonian boundary term?
From the Gauss law perspective.
Yes. This was just a physical statement that you can measure the energy at infinity. It's the Gauss law that we are familiar with, which is that when we want to measure the energy in gravity, and only in gravity, you can measure it at infinity. You can't do that in any other theory. It was a very simple statement.
Okay. Yeah. Thanks. One more question.
Yeah.
If the Hilbert space is dense as is claimed, then if I think of some state which has this normalizability and nice properties and can be included in the Hilbert space, then I can always create some projector from that state, like let's say psi and psi will be the projector.
No. Sorry. Yeah. You can create a projector from the Hilbert space. Yes, go on. Yeah. But it will not be an element of your algebra that you're defining as A epsilon generally.
Yeah, that's what I was trying to ask. Yeah.
Yeah.
If
So
I know
indeed,
about some.
yeah.
Yeah, go on, please.
Yeah. So the question is, even in local quantum field theory, you can act with an operator and create the state, right? But that doesn't mean that the projector onto that state becomes an element of your algebra, right? You see, even in local quantum field theory, as I said, it's true that you can act with an operator on some time band and in a small time band on the vacuum and create the algebra and create a state. But the projector on that state doesn't become an element of this time band. Okay, so there are two very different things here. One is, if you're given the vacuum, can you find an element of the algebra that acts on the vacuum and creates a state? And the second is, is the projector on the state itself an element of your algebra? And that only happens in a theory of gravity. It would not happen in the absence of gravity.
Yes, so in the presence of gravity, as was the last proof, I think. So for such states, this is possible because of the p omega that you.
Yes, because of p omega. Yes.
Okay. Thanks. Yeah.
So was there a question, or I couldn't?
That was the question.
Right,
I think in case of gravity, you can actually include that
right.
in the.
Right.
Yeah.
That's right.
Thanks.
Okay. Any other questions? Okay. If not, let's thank Suvrat once again, and then we continue tomorrow at 11:30, right? So the same time.
Okay.
Yeah, I think so. I will confirm.
Okay.
Okay. Bye. Thanks, Suvrat. Bye. But so we will meet at 2:30 for Ruji's. Yeah.
Okay,
Bye.
thanks.
Okay, yeah, so let's meet once again, maybe around 2:15 or 2:20.
Okay. Bye, everyone. Bye.